All right, so today we are going to finish up forward biased PN junctions and then talk about reverse biased PN junctions, and then that should be enough physics for you guys for a while. So starting on, I believe, Friday, we'll start dropping diodes into circuits and learn how to analyze those guys. All right. Give myself room to do what I need to do here. So, we've talked about what's happening under a forward bias condition, where we have these excess electrons or excess minority carriers on the P side, and we have excess holes, again, excess minority carriers, on the N side of the junction. So mathematically, the excess carrier concentrations are Pn0 is equal to pp naught times the exponential function negative q v naught minus vf divided by kbt. So this is effectively just using Boltzmann statistics to say, well, if we have a majority carrier hole concentration on the P side of the junction, then the probability of carriers diffusing to the N side of the junction is this. And similarly, we can have NP naught, so this is just the concentration at the edge, the whole concentration at the edge of the, the electron concentration at the edge of the P side is N naught exp negative Q V naught minus VF divided by KBT. If we simplify these to observe only the effects of the applied voltage, our hole concentration becomes Pn naught exp Q V forward bias divided by KBT, and our electron concentration looks like NP naught exp times that same argument. So what this is specifically talking about then is the concentration at the very edge of the depletion region. So we're not looking at how it's decaying, because if you notice, Q, VF, and KBT are all constants, right? So this, yes, pausing it. Let's see if I can do that. Better. All right. So this is just telling us what our concentration is at the edge. All right. So for long junctions, now we're going to talk about carrier diffusion. Oops, that is not what I wanted to do. Where is the pen thing? All right. So I'm going to draw a little picture here real quick. here's the, and this is kind of just like a zoomed in view of our concentrations at our junction. So, or at the boundaries of our space charge layer. Let's see, so for electron concentrations, I've been using red. And for hole concentrations, I've been using blue. Something like this. We're saying that the change in the hole concentration here is simply going to be the hole concentration on the inside of the crystal as a function of distance away from the end side of the space charge layer minus the carrier concentration that was already there. So Pn naught in this case is the holes due to the doping of the N side. And over here, we're going to have delta NP as a function of XP, the distance measured in this direction away from the edge of the space charge layer is NP of XP minus NP naught, where the height of this guy is NP naught, or excuse me, delta NP at 0, and the height of this guy is delta Pn at 0. So I'm just trying to explain effectively where all our different mathematical terms are about to come from, because we can see that there is a concentration gradient, which means we are going to observe some diffusion current flowing. So I'm going to rigorously define our carrier concentrations here then. So delta P sub n, what the heck happened? As a function of x sub n is Pnxn minus Pn naught, which is simply going to be delta Pn at 0 times exp of negative xn over LH, where LH is the mean free path for electrons in the crystal. So that's the average distance an electron can travel before it occurs, before a scattering event occurs. Then we are going to have delta NP is equal to NP of XP minus NP naught is delta NP at 0 times the exponential function negative XP over L, sorry, sorry, I made a mistake here. This should be P, and it's for holes, because this is the hole concentration equation. And This is Ln is the mean free path for electrons. So the subscript n there is correct in our top equation because these carrier concentrations, this is the whole concentration on the n side of the crystal, so it makes sense that we're moving in the xn direction. And it should be x sub p on the electron concentration because we're looking at the minority carrier concentration on the p side of the crystal. All right, so now that the minority carrier concentrations are well defined, this allows us to determine the diffusion current density, right? So the diffusion current density for holes, don't need that, is negative Q dP dPn of xn with respect to xn is negative Q dP d delta Pn of xn with respect to xn. And do I have enough room here? I think so. Is going to be Q dP over LP delta Pn at 0 negative xn over LP. So we're just doing simple substitutions in here. When we take the derivative of this guy, obviously the constant terms are going to go away. Similarly, the diffusion current for electrons, I'm just going to jump to the result here because the derivation is exactly the same. Negative Q dN over Ln delta NP 0 negative XP over LP. So these are our diffusion current densities, and there's one thing that we need to point out here. It appears as if the current flowing through the device is location dependent. And that's not entirely true, or actually not true at all in this case. The total current flowing through the device should be constant. So if I drew a picture, which it'll have to be on this page, let's see right here. Let's put negative WP. So this is the edge of the space charge layer on the P side. This is the edge of the space charge layer on the N side. If we, let me use red for electrons. We should see that the current as a function of position does something like this. So this is the diffusion current from electrons. And then on the P side, we're effectively going to have the opposite. So this is our whole diffusion current density. And if we add these currents up, they give us a constant value of current across the crystal. So this is JD total. Just to be super clear here, these top bits are from majority carrier diffusion. And these bottom bits are from the minority carrier. All right. So if we assume that recombination does not occur in the depletion region, we can determine the total current flowing through the device. So J diffusion was Q DH, sorry, DPLP, using old notes, and that's why it's confusing me. Delta PN naught is equal to Q DP LP PN0 minus PN naught is equal to Q DP LP PN naught EXP Q VF over KBT minus PN naught. Finally, our result for our holes is E DP LP EXP EVF divided by KBT minus 1. And doing a similar derivation for electrons, where we need to recognize that the direction of electron flow is opposite the direction of hole flow. So we're going to have a negative sign. We would wind up getting negative dN over Ln sorry, I missed a term here, so I need to tack on PN naught right there. Sorry about that. So dN Ln, this should be a Q, NP naught exponential Q VF over KBT minus 1. And our total diffusion current density, which is what we're really trying to find here, is Q dP divided by LP PN naught plus Q dN over Ln and P naught times exp q Vf divided by kBt minus 1, which is the same as q ni squared dp over lp nd plus dn over ln and a exp q vf divided by kBt minus 1. I promise we're almost finished. So this guy right here is known as the Shockley or ideal diode equation. It is much more frequently expressed as J diff total, JS naught or JS exp e to the VF divided by kBt minus 1. So this is the ideal diode equation that we're going to be using throughout this class. Now I'm going to take a very quick aside. We went through all of this stuff, all of this big derivation. Your web work real quick. Maybe thinking to yourself, gosh, that was a terrifying amount of math. You wouldn't be wrong. No, not this one. That one. We can use the ideal with that. But, this guy right here. Okay. So this problem, based on what we just learned, should actually be extraordinarily trivial. There is a way to do it using a crap ton of math. Okay. But I want us to think about what we have just learned, all right? So it says that we have two diodes in parallel, D1 and D2, and they draw a combined current, I total, of 15 milliamps, okay? If D1, now it's not explicitly stated here, but diode D1 and the diode D2 are otherwise identical, except that D1 has twice the cross-sectional area D2, which means they have the same mean free paths, the same sector concentrations, the same donor concentrations, the same intrinsic concentrations, and all that kind of stuff. So if if ID1 has twice the cross-sectional area of diode 2, what do we know? Based on what we just learned. If all of the other parameters are the same, the only thing that's changed is D1 has twice the cross-sectional area, then what is the ratio of the currents flowing in the diodes? So if we circle back here, and diode 1, they both have the same amount of forward bias voltage, all that kind of stuff. If they have the same intrinsic carrier concentration, the same diffusion coefficients, the same mean free paths, the same doping concentrations, they're obviously operating at the same temperature, the current density should be the same, right? Anybody got any problem with that? So if all the numbers are the same, the current density for diode 1 and diode 2 should be the same. If we want the current, not the current density, what do we do to this? We multiply it by the cross-sectional area. So I ask you again, if diode 1 has twice the cross-sectional area of diode 2, what's the current, what's the ratio of the currents there? 2 to 1, right? So ID1, diode current 1 is going to be twice as large as diode current 2, which means ID1 is 10 milliamps and ID2 is 5 milliamps. There is a significant mathematical derivation of figuring out a mathematical relationship to prove just that, but we can do it using common sense because we know how the diffusion current densities come about, okay? So I just wanted to do a quick aside there. We're developing relationships to where you can struggle through a crap ton of math on your own, or you can let me struggle through the crap ton of math for you and get to a nice and neat result, okay? All right. What time? So I've already spent 30 minutes. All right. So, okay. Circle back around here then. The next thing that I want to talk about is diffusion capacitance. So, under forward bias conditions, we have observed an excess of minority carriers in the neutral NNP region of the junction. The excess carriers cause a net charge to be stored in the neutral regions that's not how you spell neutral. Which depends on the applied voltage. So from this, we should observe a diffusion capacitance. Due to the excess charge storage. Still can't draw a Q because I'm so used to doing thetas. So, total charge accumulated on each side is simply the amount of charge accumulated on the inside and the amount of charge accumulated on the P side, which is given by Q A Ni squared Ln over Na plus Lp over Nd multiplied by that same factor, exponential of Q V forward divided by KBT minus 1. From this, we can easily determine the diffusion capacitance. So it's going to be the derivative of Q with respect to V. And so that is simply Q squared A times Ni squared divided by KBT Ln over Na plus Lp over Nd QVF divided by KBT minus 1. That's it. That's all we're going to talk about, the diffusion capacitance. I just want you guys to be very aware. This is a capacitance mechanism that is entirely separate from the junction capacitance that we talked about previously. This capacitance only arises in forward bias conditions because of the minority carrier injection that is occurring. So the junction capacitance is because of the uncovered bound ions in the space charge region. This capacitance is due to the presence of diffused charge carriers inside the neutral regions, inside the P and N region, the neutral N and P region of the crystal. So it's an entirely different mechanism by which capacitance occurs. All right, so I think that is enough for forward biased PN junctions. So now let's talk about reverse bias PN junctions. Let me zoom out here. It's going to grab me nuts. All right. All right. So in a reverse bias PN junction, we have our basic PN junction. Oh, I didn't do attendance. Thank you, Ivan. For everybody who's on the Zoom, just type something in chat, please, so that I'll know that you're here. Three of 6. That's better than I would have thought. All right, 4 of 6. Cool. All right, so we have our crystal. This is our neutral P region. Here is our neutral N region. We have bound negatively charged ions over here and bound positively charged ions on the N side of the junction. And just to be clear, this is WP naught. This is WN naught. This is 0. We have a metallurgical junction. All right, so if we apply a voltage opposite the polarity that we did for our forward bias junction, such that the positive polarity is attached to the N region. I'm saying VR for reverse bias. So that means that, so in this case, VR would be considered a positive voltage quantity. And we are just flipping the polarity so that the positive polarity terminal is connected to the N region and the negative polarity terminal is connected. So what's going to happen when the holes in the neutral P region see an excess of electrons at that terminal? Yeah, it's going to attract them. So all the holes, neutral P region, or a large number of holes in the neutral P region, will be attracted to the electrons over here, which is going to cause the width of the space charge layer to increase. If we increase the charge stored on the P side of the junction, we have to increase the charge stored on the N side of the junction as well. So effectively, all the electrons are attracted to the positive polarity terminal. All the electrons in the neutral N region are attracted to the positive polarity terminal. All of the holes in the neutral P region are attracted to the negative polarity terminal. The depletion region width increases. What does that mean with regards to the probability that diffusion is going to occur? Any thoughts? So when we had forward bias conditions, okay, so before we even get there, what's that going to do to the electric field? It's going to go up, right? If there's more charge, then the electric field, the magnitude of the electric field is going to go up, which means the magnitude of the barrier potential is going to go up, which means the probability of diffusion has gone way, way down. So we should see almost no current flowing through, okay? What's going to happen to the junction capacitance? So if the distance between the plates, where the plates are the edges of the space charge layer, if they're moving further apart, does the junction capacitance go up or go down? It goes down, right? For a parallel plate capacitor, C is equal to epsilon A over D. Well, D is increasing, so the capacitance is going to go down. All right, so now we've effectively discussed everything that's going to happen. Now let's mathematically describe those phenomena. All right. All right, so in a reverse biased PN junction, electrons are attracted to the positive polarity terminal of our voltage source, and holes are attracted to the negative polarity terminal. This attraction causes the space charge layer to increase in width as W is equal to twice epsilon over Q NA plus ND over NA times ND times V naught plus VR, where VR is the reverse bias voltage. Okay. So really, under any bias condition, what we had for the equation that we had for the depletion region width that we derived in the forward bias will work. We just treat reverse bias voltages as negative, right? So for forward bias, it had the exact same equation, except it had V naught minus VF. Well, reverse bias voltage is of the opposite polarity, so that's why we're adding it in this case. So the same exact equation works, all right? This increase in W causes an increase in the electric field E, which in turn increases the barrier potential. Meaning it will be more difficult for electrons and holes to diffuse across the space charge layer. So pictorially, something like this. Let's see. So here's our depletion region with W. This is our XP direction. This is our XN direction. We have a large field oriented from the stored charge. We get more charge these should all be positive. And our carrier concentrations are going to look like this. So there's our electron concentration. Here's our whole concentration. So all right. So what we are going to observe is that minority carriers can diffuse pretty easily, but majority carriers cannot, right? So let me clarify that. In the forward bias condition, the lowering of the barrier potential meant that it was easier for holes to diffuse from the P side to the N side was easier for electrons to diffuse from the N side to the P side. Now we're going to see effectively that electrons can diffuse into the space charge layer and holes can diffuse into the space charge layer. And it's because, so this is a very strong field, right? And electrons move in the direction opposite of the field. So we are giving electrons here a large push. And similarly, holes move in the same direction as the applied field. So even though there's a barrier potential, we're giving these minority carrier holes a large push. So we should see some current, but it's going to be really, really small because on the edge of the space charge layer, the carrier concentration, the minority carrier concentrations are very, very small. So this is what's known, so let me write this down. So we have electron diffusion in this direction, hole diffusion in this direction, and this process is what's called minority carrier extraction. So in forward bias, our current is due to minority carrier injection. In reverse bias, our current is due to minority carrier extraction. So diffusing minority carriers are swept through, so a high amount of energy is imparted to them. This process is known as minority carrier extraction. All right, so in this, minority carrier concentrations are unable to be replenished by opposing diffusion of majority carriers, okay? So we're sweeping them through, but they can't be replenished. That's why they're falling down at the edges of the space charge layer. This current is given by Q Ni squared dP over L P and D plus dN over Ln and A times exp negative Q VR divided by KBT minus 1. So it is the exact same Shockley diode equation, except that now the applied voltage is in the opposite polarity, which means we should see exponentially smaller currents. If we apply, so if VR is greater than KBT over Q, so VR is more than a few thermal voltages, which at room temperature thermal voltage is approximately 26 millivolts, what happens to that exponential function? Yeah, it approaches zero. It gets smaller and smaller and smaller because it's a negatively decaying exponential. So when VR is much greater than a few thermal voltages, our diffusion current density just approaches the constant portion here, which is known as our reverse bias saturation current density. Okay, this is the exact same JS or JS naught that we saw for the forward bias. So this is the constant that determines how current flows in a PN junction, either in reverse bias or forward bias. Like this is the characteristic, and then this exponential response is telling us how it grows when we're in forward bias. So the reverse bias saturation current density depends on the semiconductor material because it's dependent on the diffusion coefficients, which are in turn related to the electron and hole mobilities, but it is not dependent on the voltage applied. It's also strongly temperature dependent because it depends on the intrinsic carrier concentration, which should vary with temperature, but as I'm sure some of you got frustrated to find out working homework 1, the two problems where the temperature was not 300 K, you were expected to use the NI for 300 K for some wildly dumb reason I do not know. So I apologize for any frustration that came from that because it frustrated the hell out of me too until I looked in the source code and saw what was happening. So anyway, so this guy is temperature dependent and it is dependent on the material properties. All right. So blah, blah, blah. 854, let's talk about depletion layer capacitance and then breakdown, and then we'll be finished. Next page. So as we saw earlier, this charge stored in the space charge layer or the depletion region led to an unbiased junction capacitance of epsilon A times the square root of 2q over 2 epsilon times, let's see, ND, NA over NA plus ND times 1 over V naught. Right? When we apply reverse bias, this simply means the only thing that we're going to change is the barrier potential. Plus ND times 1 over V naught plus VR. This is a bit cumbersome, and so it's more often expressed as Cj naught divided by 1 plus VR over V naught. So typically speaking, you would calculate the zero bias or unbiased junction capacitance and then use that value to see how it scales with this simple term. All right. So this is the governing equation for what's called a varactor diode. A varactor diode is simply a diode which acts as a variable capacitor. So in your radios, like in your car radios and stuff like that, That's how you're able to tune to different stations, is because there's a simple varactor diode circuit in there that allows you to tune to different resonant frequencies because of the voltage variable capacitance relationship for this device. So anyway, just a quick aside. I did like 1/3 of my PhD was making a varactor, but not a diode. It was a MEMS device. All right, so this is how our depletion layer capacitance changes with reverse bias. Obviously, technically, if we put BF in here, because when we do a forward bias, right, that's going to shrink the size of the depletion region. So we should see that it changes there too. But the size of the junction capacitance in a forward bias case is typically dwarfed by the diffusion capacitance, so we don't really need to worry about it. But we could use this exact equation or this exact equation to get our forward bias junction capacitance as well. All right, last topic, and then we're getting out of here. Reverse bias breakdown. Let me ask you guys a quick question. Did you talk about energy band structures in 334 at all? Okay, that will make this slightly easier to understand then. All right. So we have previously found that under reverse bias conditions, a small, on the order of micro to picoamperes, voltage independent current flows. I'm talking about JS0. At a point where VR is equal to what we're going to call VBR, a phenomenon called reverse breakdown, So if we looked at the IV curve for a diode, where this is I, and this is V. Let me use, I don't know, purple. Purple sounds good to me. When we forward bias it, it's going to look something like this. So it's going to start slow and exponentially increase as our applied bias voltage gets larger and larger. If we make our voltage too much, we overheat it and it burns out. For reverse bias, it's going to be practically zero, incredibly, incredibly small, until all of a sudden it isn't. It's going to shoot like very, very large values of negative current. And this occurs when VR is equal to VBR. And this large amounts of current occurring under reverse bias is called reverse bias breakdown. There are two mechanisms in which reverse bias breakdown occurs. Zener breakdown, which is effectively intentional reverse bias breakdown, and then avalanche breakdown, which is not intentional. So Zener breakdown is used in Zener diodes, and we'll talk about those later in this class. Avalanche breakdown, effectively, what it boils down to is you've put so much, the electric field inside your crystal is so high that scattering, so anytime an electron hole pair is generated, when that in the space charge layer, they have so much energy that they cause other electron hole pairs to be generated during scattering events, and it just cascades out of control. We'll talk about that in a second. All right, so Zener breakdown. If we dope both sides of the junction very heavily, we can expect the depletion region width, W naught, to be very small. If we then reverse bias the junction, such that the width in negligibly, we have a system in which electrons in the valence band of the p side have the same energy as empty states in the n side of the conduction band. Graphically, with a simple energy band structure, would look something like this. So any electrons that we have here, so this is energy band valence on the p side, and this is the energy level associated with the conduction band on the inside. Electrons can tunnel across that very small distance, and we observe that current flows, because we're putting, and when we put electrons into the conduction band, we're expecting current to be able to flow. So this is p side, and this is the inside. So this is what's occurring during Zener breakdown. Okay. For avalanche breakdown, in a lightly doped junction, probability of tunneling is negligible. because the width of the space charge layer is too large. So instead, if an electron diffusing from the p side reaches the depletion region with sufficient reverse bias voltage, the electric field will be large enough to impart enough energy to break the covalent bonds of the lattice structure, generating an electron hole pair. So if I draw a picture, which will probably make this a bit easier to understand what's going on. So here's my junction. And then we've got this guy very deeply reverse biased. So let's say that I have an electron that diffuses over. It, because the electric field strength is very, very large, it could hit a portion of the crystal lattice. And bang, a pseudo explosion inside occurs, which causes the generation of another electron and a hole. Well, if this electron hits another lattice point, we get another explosion, which generates an electron and a hole and so forth. And that system just cascades out of control, which is why it's called an avalanche breakdown. So we're literally imparting the charge carriers with enough energy to break the covalent bonds of the lattice itself. And that causes an avalanche breakdown. Let's see. So if the generated electrons and holes created by the scattering events gain enough energy to create additional electron hole pairs, the rapid generation of carriers in the depletion region results in a large negative drift current. So that E field is going to sweep the electrons in one direction, which is causing a large amount of current. So that is avalanche breakdown in a nutshell. All right, we're 5 minutes early today. So let's look at the Webwork problems real quick. So problem 4, we've talked about, it was pretty easy. Problem 1, you should be in a position to be able to solve that now. It's a reverse bias PN junction with a particular cross-sectional area, and you're giving the dopant concentrations, you want to find the junction capacitance. So that should all be fair game. Next problem, this guy, technically you're ready to do it, but it may not be obvious as to why, so it may be best to hold off on that guy until we talk about putting PN junctions in circuits on Friday. And then problem 3 depends on the constant voltage model of a diode, which we have not yet covered. So problem 3 is for sure wait until after Friday to do it. All right, so 1 should be trivial, 4 should be trivial, 2 requires a little bit of thought, but you could get there. 3, leave it the hell alone. All right, see you guys on Friday. Please return the roll sheet to me.